as for the proof of it, what we are going to do is, let us assume that the maximum of u, so we are assuming that d union del d, that is your d bar, this we will call it the closure of d, right? This is the closure of d, this is just a name. This is the boundary of the domain, and this is your open and connected domain, and open, connected, and bounded again, connected and bounded. So all of those properties are there of d. Clear? Del d is the boundary. If you put it all together, that is going to be closure of d, which is again closed and bounded. Closed and bounded. Is it okay? Okay, so let's say the maximum of u, and on del d. See, del d is again closed, only just the set del d, that is closed set. And since it is u is continuous on del d, so the maximum is attained also, right? And let's just call that maximum to be m. Is it okay? Now let's say that we were saying that, you see, we are saying that the maximum of u has to be attained on the boundary, right? So let's say that on the contrary, assume that the maximum of u over d bar, so d union the boundary, let's say that is m naught. One second. Yes, that is m naught, and that is actually attained on the interior somewhere, where x naught y naught is in t. Yeah, so this is our assumption. What we are doing is this. See, we are saying that the maximum is attained somewhere on the boundary. If this is not, and of course, see, there is a maximum. If you just restrict u to the boundary, there is a maximum which is m. Is it okay? Now the thing is, what we are saying is this. According to the theorem, the maximum is attained on the boundary of d, so it cannot be attained on the interior. Is it okay? Let us say that it is attaining on the interior. So basically there is a point x naught y naught which is in the d set d, where the maximum of u is attained. Let's just assume that. Clear? If that is assumed, clearly with this assumption, clearly m naught, yes, this is greater than m. It has to be, yes, because otherwise you see, if this is not true, if there is no such m naught, then m will be maximum, which is our theorem, so that will be a contradiction, right? So m naught is greater than m. Now with that in mind, let's see that we consider a new function. Yes, so consider the function, and what is the function? It is given by v of xy is u of xy plus m naught minus m by 4r square, okay, and then x minus x naught square plus y minus y naught square. It's okay. This is just a function. So what I am doing is this: u is already given to us. I am taking u and I am adding a positive function. So see, this is basically the distance between xy and x naught y naught. This point xy and x naught y naught. Okay. So I am defining a function v at the point xy to be u of xy plus some constant. This is a constant, right, which depends on capital R. Constant times the distance between these 2 points, right? Of course, the square of the distance. Yes. So essentially v is u plus a positive function, and what is the property of the positive function? Then essentially that's the distance between the function where we are evaluating the point minus x naught y naught. What is x naught y naught? It's the interior point when the maximum is attained. Clear? Okay. So with this thing in mind, what we have is this. See that one thing. Yeah. What is r? Let me just write down where r is the radius of the circle, is the radius of a circle containing the domain D. Clear? D is open, right? Sorry, D is bounded, right? So it must be contained in some circle, big enough circle. Let's just call that radius of that circle to be choose any one of those circles and let us just assume that the radius is r. Therefore, what is v of x naught y naught? Let's just calculate what v of x naught y naught. It is u of x naught y naught. Okay, plus this thing, if you put it together, you see m naught minus m by 4r square. Yes, and this property x naught minus x naught square plus y naught minus y naught square, this is going to be 0. So basically this term is not there, this term is gone. Okay, so this is equals to m naught. This is given to us. Okay, so v of x naught y naught is again m naught. We have also that v of xy, v of xy is dominated by m. Yes, because u is dominated by m plus m naught minus m by 2. Is it okay? So that is actually going to give us half times m plus m naught. Is it okay? Which is dominated by m naught on the del d. Yeah? Del d. Okay. I hope this is clear. See, boundary, on the boundary, if you restrict v on the boundary, what happens? First of all, v equals to u plus this particular function. So u on the boundary, you see, u on the boundary has a maximum m. So essentially this u can be dominated by m on the boundary. And what about this particular term, this second term? Second term is, if you think about it, this particular term on the boundary, x minus x naught square plus y minus y naught square, yeah, that is essentially your r, right? Yeah. So what happens is, if you cancel it out, basically 2r, right, in this case. So if you cancel it out, it becomes m naught minus m by 2. Okay, see, this is a r is the radius of the circle which contains d naught, right? So x naught xy minus xy, this xy minus x naught y naught, that is what is the the distance between that is r square. So basic, if you calculate that, that is going to be if you can cancel it out, this is going to be, so one second, let me do it to be 2. So this is r square. If you cancel it, it becomes m naught minus m by 2. So which is half m plus m naught, which is again dominated by m naught because m naught is greater than m, right? So v of xy is less than m naught on the boundary. Okay, now thus v of xy, okay, attains its maximum at a point in the domain D, right? See, this is a continuous function, that's a continuous function. Sum of two continuous function is going to be continuous, right? So v is also continuous up till the boundary, and since v is continuous up till the boundary, it attains a maximum at a point in D. Okay, because of this. Clear? Okay, therefore by definition, what you have, vxx plus vyy, if we do vx plus vyy, that is going to be uxx plus uyy, that is via linearity, right, plus the derivative of this particular term, that is, if you can calculate it, please do it yourself. You can show that this is equals to m naught minus m by r square. Yeah, so which is nothing but m naught minus m by r square. Yes, this is positive. Yes, so but you see, v is a maximum, so basically the maximum of v is attained in D, right? So therefore vxx plus vyy, vxx should be less than equal 0 and vyy should be less than equal 0, right? Which implies vxx plus vyy should be strictly less than equals to 0. That's a contradiction. Okay, I hope you know why this is true. Okay, let me just do it again. See, let's say v attains its maximum at a point on the inside the domain D, right? So if there is a maximum then you know that gradient of v is going to be 0. So essentially that will give you that v is a critical point. Yeah. Also, if v is 0, this is a maximum, then the second derivative, the Hessian of v, yeah, that is negative definite, right? Negative definite. Okay, what does it mean? It means x transpose d square v, this matrix times x, this is going to be less than equal 0. Clear? So for all x in R2 minus 0. Okay, so if you choose x to be 1 0, then this actually turns out to be vxx. Okay, if you take x to be, so maybe I should write it like another x naught for all x naught in this. So if you take x naught to be 1 0, it becomes vxx, which is negative, and if you take x naught to be 0 1, yeah, then it becomes vyy, yeah, which is negative, which is negative. So in this way, vxx and vyy are both negative. If you add it up, it becomes negative. But here you are actually calculating that this is positive. That's a contradiction, and hence what happens is we can actually say that the maximum, yeah, since if the function is harmonic, then the maximum of a harmonic function has to be attained on the boundary. Is it okay? Now, with this in mind, we can also talk about the minimum. So similarly, you see, whatever we have talked about, similar sort of thing you can actually go on doing, right? Principle. So this is called minimum principle, and you can say that the minimum of a harmonic function. So if u of xy is harmonic in some domain D, right, and continuous on D bar, yes, then u attains its minimum on the boundary of D. Is it okay? Yeah. So what I am saying is this: in both the cases, since harmonic function is true, the maximum and the minimum, both of them has to be attained on the boundary of it. Yeah. Now proof of this, I want you to do it yourself. The proof, what you do is you change u to minus u. So basically the minimum of u becomes the maximum of u, and then you use the other theorem, this maximal principle, this theorem, and then you get a answer that the maximum has to be attained on the boundary. So if minus u attains maximum on the boundary, it means u attains the minimum on the boundary, right? And then you are done. So basically you can just use that fact. Okay, so so this is maximum and the minimum principle. This holds for harmonic function. So what is a harmonic function? So if Laplacian u equals to 0 on the boundary, yeah, then the maximum of u and the minimum of u will be is attained, sorry, this is on T, is attained on the boundary of T. Is it okay? Provided u is C2 omega. C2 omega is inside every, it is twice continuously differentiable, and on the boundary it is continuously differentiable. Not omega, D union C T bar. Is it okay? So up till continuous, up till the boundary, if that happens, then the maximum of u is attained on the boundary, and the minimum of u, that's your maximum principle. Yes, there are other, some applications of this maximum principle, and the first application which we are going to do is this application is called the uniqueness theorem. So as I told you, it is one of the most fundamental things which you can learn in all of PD maximum principle. So the first is uniqueness theorem. What does it say? It says the solution of the Dirichlet problem if it exists is unique. See, the thing is, again, as I told you, this is a a priori estimate. We don't know whether the solution exists or not. Without knowing, we are telling something about the solution. So essentially what we are saying is this: we don't know whether the solution exists, but if it exists, it has to be unique. So let's look at the proof of it. Very, very simple proofs. So let's say that two solutions are there, u1 of xy and u2 of xy. u2 of xy are two distinct solutions. Two distinct solutions in what? In which space? C2. C2 means twice continuously differentiable in some domain D, union C D bar. D bar means it is continuous up to the boundary. Okay, so let's start with two distinct solutions in this space. Yeah, now then u1 and u2, so distinct solutions, right? Then u1 and u2 satisfies Laplacian of u1 is equals to 0, u1 equals to f, right? So this is in D on the boundary, clear? And again Laplacian of u2 is equals to 0 and u2 is equals to f on the boundary in D, clear? Now if we add those two up, therefore what happens is, now subtracting, see, since u1 and u2 are harmonic in D, in the domain D essentially. Okay, so that will imply that u1 minus u2 is also harmonic, in D, right? Very easy to see, because Laplacian of u1 minus u2, you can see it is nothing but Laplacian of u1 minus Laplacian of u2. This is 0, this is 0. So basically u1 and u2 are also going to be u1 minus u2 is also going to be harmonic. So what does it say? It says that if you have two harmonic functions, if you consider subtracting, there is also going to be harmonic function, clear? Okay, so u1 and u2 is also going to be harmonic in D. Yeah, and moreover, if you see what u1 and u2 does in the boundary, it becomes 0 on the boundary. So essentially in D, inside D, what happens is, it is a harmonic function u1 minus u2, and u1 minus u2, that function is going to be 0 on the boundary. Okay, so what is the maximum and minimum principle says? And minimum principle says, principle implies that both maximum and minimum of u1 minus u2. So u1 minus u2, you can think of a function phi, which is u1 minus u2. And what does phi satisfy? Laplacian of phi equals to 0 on in the domain D, and phi equals to 0 on the boundary of D, right? Now maximum principle we can assume here, use here maximum principle. It says that the maximum of phi is attained on the boundary. Phi is always 0 on the boundary, so the maximum of phi is going to be 0, right, over the whole domain in D bar. D bar is what? D bar is D union the boundary. And again the minimum principle also says the minimum is attained, and since the function is 0 everywhere, so minimum of phi is also going to be 0 in D bar. So the maximum and minimum of D is always going to be 0. What does that imply? That will imply that phi is 0, right? It means that phi is going to be 0. Yeah, so it means that u1 is equals to u2 here in D bar essentially, yeah, D bar, which is nothing but D union the boundary of D, and hence the uniqueness. So hence proved. Yes, proved. See, it is very easy, right? It is very, very easy. So this is a small remark which I want to make. Small remark. You have to check this part. I did it for a harmonic function, but can you show this sort of thing, that Laplacian u equals to minus Laplacian of u equals to 0 has at most one solution. At most one solution. Subject to Dirichlet condition, Dirichlet boundary. Okay. So what I mean is this equation, minus Laplacian u equals to f in D, and u restricted to the boundary of D is, let's say, G. Yeah. So this is your Poisson equation, right? And this equation, what I'm trying to say is, if there is a solution, that has to be unique. That's basically it. Yeah. So check this. Clear? So basically same thing. You see, if you replace 0 with another function g or f, what doesn't matter. What happens if you are subtracting, it's basically becoming 0, so all of this analysis goes through, nothing changes, right? Okay, so I will show you another property, yes, and that is the last property which I am going to show. It's called the continuity property, continuity theorem, or continuity property, whatever you want to call it, you can call it. Okay, so the solution of the Dirichlet problem depends continuously on the boundary data, yeah. See, this is the same property which we talked about when we talked about well-posedness of a problem. You remember, for a well-posedness of a problem, what do you need? Existence, uniqueness, and continuous dependence on initial data. See, this Poisson equation, let's say this equation, yeah, let's just assume that you can find a solution. We don't know whether we can do it or not. Let's just assume that we can do it. What are the other two properties for well-posedness? You need to know whether it is unique or not, and here we have already seen that it is going to be unique via Maxwell principle. And we are also saying that you can use Maxwell principle to show that the solution of the Dirichlet problem, it will depend continuously on the initial data. Yeah. So once you find a solution of a Dirichlet problem, you can actually guarantee that the problem is well-posed. Clear? So let's look at the proof of it. Again, not very difficult proof. So let's say u1 and u2 are the solutions of Laplacian of u equals to, so I am doing it for 0, yeah, a harmonic function essentially, in d, and u equals to f1 on delta d, yeah. Sorry, this is u1, solutions of u1, and this equation Laplacian of u2 equals to 0 in d, and u2 equals to f2 on the boundary of d. Is it okay? So essentially there are two, you see, f1 and f2 are the two different datas, right, which is there on the boundary. Of course, in the interior both u1 and u2 are harmonic. Yes. Now define v equals to u1 minus u2. Then if you define it, v satisfies c, it is a harmonic function again, satisfies Laplacian of v is equals to 0, right? Let me write it properly. Laplacian of v is going to be 0, yes, because Laplacian of u1 minus u2, see, since Laplacian of u1 minus u2 is nothing but Laplacian of u1 minus Laplacian of u2, which is 0. Clear? So this is in omega, this is in d, okay, and v is equals to f1 minus f2 on the boundary of d. Is it okay? So of course on the boundary there is the difference. Now you see what is maximum and the minimum principle says that the maximum of f1 and f2. So it says that the maximum and minimum are both attained on the boundary. Yes. So it says that f1 minus f2, okay, attains the maximum and minimum on the boundary, and minimum on the boundary, right? Okay. Del d, boundary in del d. Okay. So thus, see, continuous dependence on initial data means that if you are changing the initial data a little bit, your solution also changes a little bit. So thus, given epsilon greater than 0, if f1 minus f2 less than epsilon, then of course on b, on del d, then at any interior point, in d, what do you have? Minus epsilon gets dominated by the minimum of V, right? And that will be dominated by the maximum of V, and that is again dominated by epsilon on the boundary. Clear? Huh? Sorry, not on the boundary. What am I saying? So it's less than epsilon. Clear? See, the thing is the minimum of V and the maximum of V at the interior point, that is definitely going to be smaller than. So let's say the minimum of V will be bigger than the minimum of F1 minus F2 on the boundary. So V minimum should be dominating minus epsilon. Again, V minimum is dominated by V max, right? Always. And again, V max will be dominated by epsilon, right? Because the thing is f1 minus f2, what is the upper bound? This is basically epsilon. Yeah? If you want, you can take it to be greater than equal epsilon, absolutely no issues here. Okay, so this is the case. Thus, therefore, if mod v is less than epsilon in the domain D, yeah, you see, this means that mod v is less than epsilon. If v minus and v maximum always lies between minus epsilon and epsilon, it means the modulus of v is always dominated by epsilon, right, in T, and therefore mod u1 minus u2 is always getting dominated by epsilon, right? So given epsilon greater than 0, you can start, if you start with mod f1 minus f2 less than epsilon, then you can show that the solution is also sufficiently small. So you start with your initial data which is sufficiently small, and then you can show that your solution are also sufficiently close to each other. Clear? Okay, so I am going to end this video with a small question, and this is a question I want you to answer, and this is concerning this maximum and minimum principle. Again, very easy, yeah, but let's, and this is, I mean, not a very difficult question. Huh? So let's say let um be a sequence of harmonic functions. Harmonic functions in the domain D. Some domain D is given and we are having a sequence, and it is continuous on the boundary D union the boundary of D. Clear? Okay, so let Fi be the values of ui on the boundary. Clear? So on the boundary, let's say fi, so if you restrict ui to the boundary, let's say that is going to be fi, yeah, the function fi. Clear? Now if a sequence un, so this converges uniformly, okay, on the boundary del D, then it converges uniformly, okay, in the set D also. Okay, so this question, this is a question which I am posing. If you are, interested in doing some analysis kind of thing, then you can look at this question. If you know analysis, then only you can do it. Otherwise, you forget about it. It's not a part of this thing. This is just a extra thing which I want you to know. If you can do it. Otherwise, you can just leave it out. Huh? This is for advanced students. You can leave it out. So with this, I am going to end this video. Thank you.